On this channel, we provide useful programming information with practical code examples. This time, we're focusing on the concurrent module in Python. While clarifying the concepts of concurrency and parallelism, we will explain how to implement asynchronous processing using the concurrent module with practical examples. Enabling subtitles will make the code descriptions easier to understand. When speeding up processing in Python, it's important to be mindful of the differences between concurrency and parallelism. The concurrent module is an important means of safely and simply handling asynchronous processing with these differences in mind. Concurrency means designing a process so that multiple tasks proceed by switching between them in small units of work. Even if tasks aren't actually running simultaneously, making use of waiting time allows you to make the entire process more efficient. Parallelism is a mechanism that physically executes multiple tasks at the same time. By using multiple CPU cores, processing is advanced simultaneously. Both are techniques to speed up processing, but concurrency is a design issue of how to proceed, while parallelism is an execution issue of how it runs, making them fundamentally different. Concurrent is a standard library in Python that provides a high-level API to handle concurrency and parallelism safely and simply. It is designed so that you can focus on executing tasks without having to worry about low-level operations like creating and managing threads or processes. The concurrent module provides two main options depending on the nature of the task. This is suitable for concurrent implementations, especially tasks with many I/O waits, such as network or file operations. By switching between tasks, it makes effective use of waiting time. This implementation is aimed at parallel processing and is suitable for CPU-intensive tasks. It uses multiple processes to take full advantage of available CPU cores in parallel. Thus, a main feature of the concurrent module is that it provides a structure that allows you to properly choose between concurrency and parallelism as needed. ThreadPoolExecutor is suitable for I/O-bound tasks, such as network communication and file operations. It distributes tasks among multiple threads, making effective use of waiting time. In this example, multiple I/O tasks that wait for 1 second are executed concurrently. By using submit, function calls are registered as asynchronous tasks, and by calling result, you can wait for completion and get the results, allowing you to implement concurrent processing that makes effective use of waiting time in a concise way. If complex control is unnecessary, using map can make your code more concise. In this example, multiple I/O tasks are executed concurrently using ThreadPoolExecutor.map. Since map returns results in the same order as the inputs, you can write code close to sequential processing, and concurrent execution is possible without being conscious of asynchronous processing. This is a major advantage. For heavy computations that fully utilize the CPU, you should use processes rather than threads. This allows you to avoid the global interpreter lock (GIL) limitation. In this example, CPU-intensive computations are executed in parallel using ProcessPoolExecutor. Because creating processes is involved, a main guard is required, which enables safe parallel processing utilizing multiple CPU cores. As completed is useful when you want to handle results in the order they complete. In this example, multiple asynchronous tasks are executed simultaneously, and results are retrieved in the order in which they complete. Using as completed lets you handle results quickly regardless of task order, making it suitable for progress display or situations requiring sequential handling. In concurrent, exceptions are raised when you call result. This example demonstrates that even if some tasks raise exceptions, the others continue execution and you can handle exceptions individually when retrieving results. By using concurrent future, it's important that successes and failures in asynchronous processing can be safely handled. To use concurrency and parallelism effectively, it's important to choose the right approach based on the nature of the task. In practice, the following criteria can help you decide. For processes with a lot of I/O weights, such as communication or file operations, use ThreadPoolExecutor. For CPU-bound, heavy computational tasks, use ProcessPoolExecutor. If there are many simple tasks, using map allows you to write more concise code. If precise control over execution order or exception handling is important, combine submit with as completed. By using the concurrent module, you can handle asynchronous processing safely and intuitively. The main benefits are as follows. You don't have to bother with low-level thread or process management. It's provided as part of Python's standard library, so you can use it with confidence. The code becomes more readable and maintainable. It's ideal as a first step in learning about concurrency and parallelism. Simply keeping these guidelines in mind can greatly reduce failures in implementations using concurrent. The concurrent module is the standard option for practical concurrency and parallelism in Python. It allows you to boost performance without greatly changing the content of your processing, which is a significant benefit in actual practice. By using concurrent, you can implement asynchronous processing concisely while safely managing exception handling and execution control. The source code for this video can be downloaded from the official website. If you like, please visit the URL in the description to aid your learning. Thank you for watching until the end. If you enjoyed the content of this channel, please consider subscribing.